Hey, what is up, everyone? Today we are going to try and answer this question: what is a sampling distribution? But instead of having that be my essential question, I'm going to change the context a little bit and try and frame it in a way that's a little bit easier for us to understand and actually have a goal in mind. And we want to know something that's a little bit more practical. And in order to do that, I'm going to try and answer this question: what makes for a good statistic? Right, we're in a statistics class. We should know what is actually a good statistic and what is it actually representing. Well, a major goal in statistics is to make an inference about a population. Unfortunately, we know that we can't measure every member of a population, so what we do is we concentrate on measuring smaller samples of those populations. But what if we could? Well, if we were to measure every member of a population about something we cared about, we would get this thing called a parameter. And so a parameter is very simply, it's going to be a number that is going to describe a characteristic of an entire population. Since it's something that's going to describe an entire population, we tend to think about parameters as the truth, since it's going to describe an entire population. So I want you to get the really big tie with these three words here to recognize, first of all, we can have a little bit of a mnemonic with parameters and population. Parameters describe populations, but really that's supposed to be the truth, since it's describing what we want to know about everyone. Unfortunately, we know that that's not always how things work. We want to know how everyone behaves, but since we can't collect that, we have to use something else, and that other thing is called a statistic. So a statistic is going to look very similar. It's going to be a number that is going to describe a characteristic, but not of an entire population. This is only going to describe a characteristic of a single sample. Right? So instead of asking 2,500 people in our entire school how tall they are, we just grab a sample of 30 people and measure their height, and those 30 people speak for the entire group. So generally what we tend to use to differentiate between a statistic and parameter is the difference between English letters and Greek letters. So we will tend to use English letters for statistics, but we're going to end up using Greek letters in general are used for parameters. So what does that look like? Well, parameters, we know what these things are, okay? When we are talking about means, we know that there's two different symbols that we use. We have mu and x bar, but mu is that Greek letter, and that describes the population mean. For standard deviation, we use that Greek letter sigma, and that's lowercase sigma, not capital sigma for some. And then proportion, well, notice here mu starts with that letter M, sigma starts with that letter S. What Greek letter can we think of that starts with P for proportion? Well, that's pi. Now, some older textbooks and even some college textbooks will tend to use pi, but since we know pi is 3.14, it has very special geometry connotations, we tend not to want to be confused with that. So what we do, we have a little bit of a change here, and we will use the English letter P for proportion. So P for population proportion. Now, what about the statistics notation that we want to use? Well, for the statistics, you guys, again, this isn't really anything new. You know what these are, even if you didn't realize what the difference was. We use x bar for a statistic, so this is talking about a sample mean. And then for standard deviation, we use the letter S. Sometimes we use the subscript x to go along with that. And then for proportions, well, the English letter that goes along with that is P, but what do we end up using? We use a hat on top of it. It's a little caret symbol above it, and we pronounce that as p hat. You're used to seeing this before. We did this with linear regression when we did y hat equals a plus bx, and hopefully the idea there was that you remembered that y hat was used to make a prediction. Well, what do statistics do? They're used to make a prediction about an entire population. So that's again where we see this idea about the hat coming from. So whenever we start collecting information, we are generally collecting statistics until we know we've collected information from an entire population. So what we've done at that point is that we have created a distribution of sample data. Okay, a distribution of sample data is a distribution of information from just a single sample that you select from an entire population. So this is stuff that you've made before. Whenever you've made dot plots or histograms or anything like that, what you've mostly been working with is a distribution of sample data. The problem is we tend to have this thing called sampling variability, right, where we know that any distribution is going to have a little bit of difference. Even if we pick very similar individuals in a population from one sample to the next, we know we are likely going to have a different sample mean, a different sample standard deviation, and a different sample IQR, a different sample median, etc., etc., etc. So if this statistic that we get from this distribution of sample data is going to vary from one sample to the next, how are we supposed to know it's reliable? How do we solve this conundrum? Well, what we do is we look at lots and lots of samples. And when we make lots and lots of samples and we look at lots of sample means, lots of X bars, lots of standard deviations, we are creating what's known as a sampling distribution. So a sampling distribution is a distribution taken by values of statistics. It's taken a whole bunch of sample means. It's taken a whole bunch of p-hats. It's taken a whole bunch of standard deviations. Okay, so a distribution of values taken by statistics in not just one sample then, but many samples, as in hundreds, thousands of samples. Every one of those samples is always going to have the same size and is from the same population. That's what a sampling distribution is. It's a distribution of all possible sample means, all possible standard deviations, all possible IQRs, so on and so forth. Whatever measurement that you want to record, that's a sampling distribution. So turning the page now, why do we care about sampling distributions? What's the point of looking at every single possible sample? Well, sampling distributions can tell us how any random sample should behave. Why is that important? Why do we care about how random samples should behave? Don't we like randomness in statistics? Well, yes, we like randomness because we know randomness tends to be reliable. And the important thing is that if we know how a random sample should behave and that sample is going to be reliable, then what it's going to do is it's going to tell us when we have something that's going to be typical or something is going to be weird. So we would say that sampling distributions can tell us if our one sample that we obtain, if our information that is gathered is going to be typical or weird. Okay? The idea behind taking a sample of a population is to be able to say something about the population as a whole. So how can we be certain that our calculations from the sample is trustworthy enough to say something about the population? To do that, well, what we need to do next is examine and describe key components of the sampling distribution. If we can describe key components of a sampling distribution, we know how it behaves. Again, we know when something is weird or when something is typical. So let's describe a sampling distribution. Well, what did we describe before with any other kind of distribution of sample data? We looked at SUCs, shape, unusual, center, and spread. We're going to start with center. Okay, so center is going to be an we're looking for an unbiased estimator when we are trying to describe the center. The center of a sampling distribution hopefully is going to be the same as the parameter that we are trying to estimate. So to formalize that definition of what an unbiased estimator is, we say it's a statistic that can be used to estimate a parameter if the mean of its sampling distribution is equal to the value of the parameter that's being estimated. So the mean of the sampling distribution, okay? This is going to be weird notation, but we're looking at lots of different kinds of means. We could be looking at the mean of some other mean. We could be looking at the mean of a proportion. We could be looking at the mean of all possible standard deviations. So there's lots of different possibilities here. We are looking at all possible proportions from a sample of a given size. What's the average sample proportion supposed to look like? What's the average sample average supposed to look like? Okay, that's what we're really trying to look at with this unbiased estimator, and hopefully we would say that this thing, mu sub p hat, the average sample proportion would be equal to a population proportion, or the average sample average would equal the population average. That's what we're looking to see if something is going to be unbiased. Okay. After that, we look at the next thing, and the next thing we would pay attention to is what's known as spread. It's our last S in our SUCS acronym, right? So when we're looking at spread, we're looking at variability, and what do we generally want? We want lower variability. So low variability from one sample to the next is better. It means if we have low variability, that each sample is going to be consistent. Each one is going to be reliable, and I can consistently rely on my random sample to produce statistics that accurately estimate the parameter. Now, I get it that your head might be swimming now, so let's pause for a second and take a look at a brief example. Alright, so in this example, let's just say, just for kicks, that 36% of people in the world, the entire world, brush their teeth every day. Okay, now again, I have no idea if this is true or not, but we're going to assume that this is the truth for the entire world. So we will call that figure P equals 0.36. At this point you might be thinking, well, wait, back in chapter 6 we said that P was probability. Well, it is kind of like probability. It's the same idea, right? What we're saying is that if I were to pick a whole bunch of people at random, 36% of those people selected would brush their teeth every day. But we're just going to give it a slightly different name at this point because we are evolving in our statistics understanding, and we're going to call this value P, 0.36, the population proportion, the proportion of the entire population that brushes their teeth each day. So what we have here are two different sampling distributions. Every one of these dots represents a different sample proportion. So this guy right here, this is a P hat. And what was the proportion of people in that sample that brushed their teeth? Looks like it's maybe about 53 or 54%. So this P hat is going to be about 54%, right? Now, every one of these is from a sample of 100 in this top one. In the bottom distribution, that obviously has a little less variability, the sample size for every one of those dots was 1,000. Now, let's try and describe and understand the two things that we want to look at. Center. Is this an unbiased estimator? Well, where's the center of this distribution? I'd say it's right about here, and that's pretty close to this center right here. Well, where are the centers of these two sampling distributions lining up? 0.36. And we say that this is the average sample proportion, or the mean of all sample proportions, because it's in the center, right? So this is the center of our sampling distribution. We call it the average sample proportion. And what do you notice about that value? 0.36. Well, that is the same value as P. So since mu sub P hat, the average sample proportion, the center of our sampling distribution, is the same as our population proportion, then we would say that this is indeed unbiased. Okay? Now, the next thing we want to look at, we talk about the spread. Well, which has the less variability, the sample of size 100 or the sample of size 1000? When we have more individuals in our sample, we will tend to have more reliable and consistent estimations. So this one is less variable, which makes sense since it's the larger sample size, and thus this is going to be a more reliable sampling distribution. If we take a sample of 1,000 individuals, it's going to more reliably, more likely make an estimate for the true population proportion of people that brush their teeth. Okay, it makes sense. Look at some of the weird samples we had. We had a sample over here that was 54% of all of those people, and a sample of 100 brushed their teeth. But we also had a sample of less than 25% of them brushed their teeth. Look at the extremes we had when we had samples of 1,000. Our range only went from about 33 to about 42%. So again, much more consistent observations in each of those samples. They're going to give us much better estimations. So now we should be able to summarize everything in just a couple of sentences. First of all, we would say that larger samples will provide less variability. And then here's a real moneymaker. So the best statistics that estimate a parameter will be those that produce something that is unbiased as an estimator. Remember, that's where the center of the sampling distribution is the same as the thing you're trying to estimate. And they're going to have the least variable sampling distributions. Okay, so take a look at the examples that you guys have next. I will have the keys posted onto Google Classroom for you. That's all for today. I will see you in just a little bit.